Let's look at the gravitational potential energy. So it's in general, the gravitational potential energy is defined as the work done by gravitational force when the object is moved from its current position to a reference position. For example, in the Earth and another object system, so m, big M for the mass of the Earth, and this small m for the object. So if the object is in this position right now, this position, so how much is the potential energy of the m? It really depending on where you set the reference. Okay, for example, let's set this as a reference. Okay, so this is a position different from the current position. Let's just set this for now as a reference. So basically, to find out the GPE the M has, so you have to calculate how much work will be done by the gravitational force when the M move from this position to this reference position. Okay, so let's label here as a reference. And also when we see the GPE of M, we're really talking about the GPE of the two masses system. Because without the big M, which is the Earth here, there's not even a gravitational force. So, and then of course there's no work done by a gravitational force. So actually GPEs actually should be always referred to two masses system. Okay, otherwise there's no GP at all. Maybe we often refer to the GP of one particular object, but you should understand it means two bodies at least. Okay, so let's focus on how to calculate the work done by the gravitational force when the M moves from its current position to the reference. So I label the distance between the two M. Okay, when we see the distance, we always mean the distance between the two center of the object, just like the R in the gravitational force formula. So the R is always between two centers. So I label this as R initial, and label this one as R final. So try to figure out the work done by this. The problem is, if you look at the graph of the force acting on the M, it's given by this formula. So because it's GMM over R squared, so you can see it's reversely proportional. So the Fg is reversely proportional to the R squared. So the graph is approximately look like this, and that means the force is a variable force when the R is pretty far away from the Earth. Of course, when the R is very close to Earth's surface, so we treated Fg as constant, right, equals mg, the g equals 9.8. But in this case, no, it's not a constant. Okay, how to find out the work done by Fg when the object moves from R initial to the R final? Okay, so this one really should equal to the area under the graph. Okay, so the area here equals the work done by Fg. Okay, so the problem is to find out the area, so we have to use calculus. So WFG, okay, should equal, so this is integration of calculus when the object from move from R initial to R final. And here should be the Fg times dr. Okay, if you have not learned the integration in calculus, this one would be difficult to understand. Now, basically, this one we call integration is used to calculate the area. Okay, but to actually get the calculation done, if you haven't learned that, you don't understand. So I just skip the process and just give you the result. So the result will be negative g m m of the r final minus negative g m m r initial. Now we do have one problem here, because we're finding the area here does not have sign, means positive. But if you understand the work done in this way, you move the object away from the Earth, and where the so that's going to be the direction of your displacement, right? Where the gravitational force is actually going to be towards the Earth, right? So when you move away, this the displacement and force having opposite direction, the work done must be negative. So that's why we need to add a negative sign here. So that's why you need to actually add a negative sign here. Okay. And then we can switch around. So actually it should be, so WFG should be negative R initial G M M minus negative G M final. Okay, it's not nice. Okay, so this is actually the work done by FG, the general formula. But a lot of students ask why the real formula is actually just having one term. It is because if you look at this, the reference is set at distance r final away from the Earth. But because the reference is really something you can set at anywhere, since it can be set anywhere, can we just set the reference position set at infinity? Infinity means it's infinity far away from the Earth. That means RF is actually approach to infinity. So that's why the negative G M M R final is actually approach to 0. Right? Okay, if that's the case, and then the WFG, which is the general formula, should just simply be negative G M M over R. Okay, so I take away the I initial because that's a general formula when the object, when M is R away from M and reference is set at infinity. Okay.